Welcome. Today, we're moving beyond the hello world of computer vision. We're not just asking what is in this image, but also where is it? This distinction between image classification and object detection seems simple on the surface, but the architectural and practical implications are profound. Understanding this difference is key to designing efficient, accurate, and scalable vision systems. It's the choice between knowing a cat is in the picture versus knowing exactly where the cat is and that it's about to knock a vase off the table. Let's dive in.
Image classification is the foundation. Given an image, the model's entire job is to assign a single label from a predefined set of categories. Think of it as a high-stakes sorting machine. The magic here happens in convolutional neural networks, or CNNs. Through layers of convolutions and pooling, the network learns to extract increasingly abstract features, from simple edges and colors in early layers to complex patterns like textures or shapes in deeper layers. The critical final step is a global pooling layer followed by one or more fully connected layers. This is where the network condenses all that rich spatial information into a single probability vector. Each element in this vector corresponds to a class, and the model essentially votes on which one class best represents the entire image. This is its strength and its fundamental limitation. It assumes one dominant subject. It can tell you there's a dog in the photo, but not if there are two dogs or if the dog is only taking up a tiny corner of the frame.
Object detection takes a significant leap forward. It doesn't just classify, it localizes. The output isn't a single label, but a list of objects, each with a class label and a bounding box, the coordinates defining its location. This fundamentally changes the problem. The network now has two jobs, classification and regression. It has to classify the object inside a potential box and regress the precise XY coordinates, plus the width and height of that box. To manage this complexity, models introduce concepts like anchor boxes. Instead of searching every possible pixel, the model places a grid of predefined boxes of various shapes and sizes over the image. It then predicts two things for each anchor: how to adjust the anchor to better fit an object, the regression part, and the class probabilities for the object inside that adjusted box. A crucial metric here is intersection over union, or IOU, which measures how much a predicted box overlaps with the ground truth box. This helps the model learn what constitutes a good detection versus a miss.
So, how does a model's architecture enable this shift from classification to detection? It's all in the head of the network. A classification model, like a ResNet 50, has a backbone that extracts features, and its head is simple. It flattens the final feature map and passes it to a fully connected layer that outputs class probabilities. The spatial information is intentionally discarded at the end. An object detection model, like YOLO or faster RCNN, repurposes that same powerful backbone, but its head is far more sophisticated. It doesn't discard spatial information, it leverages it. Instead of one output, it has multiple outputs for each location on its final feature map. Typically, it has a classification head to predict the class and a regression head to predict the box coordinates. More advanced architectures like feature pyramid networks, FPNs, go even further. They recognize that small objects are best detected in high-resolution feature maps from earlier in the network, while large objects are captured in low-resolution maps from later layers. An FPN builds a multi-scale pyramid of features, allowing the model to make predictions at different scales, dramatically improving its ability to detect objects of varying sizes in a single pass. This is a critical design pattern for robust, real-world detection systems.
Choosing between these two is a fundamental system design decision. Image classification is your tool when the presence of an object is what matters. Think medical imaging. Is this slide cancerous or not? Or content moderation. Does this image contain inappropriate content? It's fast, computationally cheaper, and simpler to train. You must use object detection when the location, count, or interaction of objects is critical. Autonomous driving needs to know exactly where other cars and pedestrians are. Retail analytics needs to count items on a shelf. Manufacturing needs to spot defects in specific locations. The trade-off is complexity and cost. Detection models are larger, require more complex labeled data, bounding boxes are expensive to create, and are more computationally intensive to run. Your takeaway is this: don't default to the most complex model. Start by defining your business problem. Is it a what problem or a what and where problem? Answering that question will guide you to the right architecture and save you countless hours of development and significant operational cost.